Let's talk about lines that intersect circles. The interior of a circle is the set of all the points that are inside the circle. So the exterior of the circle would be the set of all points outside the circle. We've talked about interior and exterior before, and it holds true for circles as well. Interior is inside, exterior is outside. Some lines and segments that intersect the circle, these will be new to you. You have a chord. Notice in the diagram the chord is red. It's a segment, so it has two endpoints that lie on the circle. You have a secant, which is a line that intersects the circle at 2 points. So what I want you to think about is, since a segment is a part of a line, could a chord be a part of a secant? The answer would be yes. It just comes down to how do you name the segment or the line. Do you name it as a chord, which is a segment, or as a secant, which is a line? You also have a tangent, which is a line in the same plane as the circle, and it intersects the circle at exactly 1 point, which is the green line in the diagram. So the tangent intersects the circle at 1 point, which is that point of tangency. The secant is a line that intersects the circle at 2 points. So what I kind of use to help me remember the difference is that secant reminds me of second. So you have that second point in order to make it a secant line in a circle. So let's look at this diagram here, and let's identify each line or segment that intersects circle L. Notice we're naming the circle based on the name of the center. So we have the circle with an L, so we know it's circle L. So look at the picture. See if you can identify any chords. Hopefully you notice that there are 2 chords here. You have segment JM and segment KM. Notice how we are naming them. We put a segment up above the letters. It is important that you name them correctly, because if you identify a secant, secant also uses the points J and M, but the difference between chord JM and secant JM is that the chord is a segment, the secant is a line. So that's what we talked about just a few seconds ago, that a chord is a part of a secant, but it comes down to how you name it. So make sure you are naming your segments and lines correctly. So see if you can identify the tangent, remembering that a tangent is a line that intersects the circle at exactly 1 point. You should notice that line M is our tangent line. What would be the point of tangency for line M? Hopefully you would put that it would be point H, because H is that point of tangency. Now look at the diameter and radii. Diameter, remember, it goes all the way across the circle through the center, and here we get segment KM. So a chord could also be a diameter, but a diameter is always a chord. So you have to look at where the chord goes through. Does it go through the center or not? Here with the radii, hopefully you notice that there are 3 of them. You have LK, LJ, and LM. So be able to identify the different parts or lines and segments of a circle. Let's talk about pairs of circles. You have congruent circles, which they're congruent if they only have congruent radii. Since the radii are all the same in a circle, you just have to know that circle A and circle B in this case are congruent because AC is congruent to BD. You have concentric circles, which are circles within a circle, but they have the same center. This would be like if you were to drop a rock in a pond and you see all the ripples going out from the rock. Those are concentric circles. Then you also have tangent circles. Just like a tangent line intersects the circle exactly once, tangent circles intersect each other at exactly 1 point. Now if you look at the diagrams, you have internally tangent circles and externally tangent circles. Internally tangent circles, you have one circle within another circle. They are not concentric. Notice you have a red center and a blue center that are not the same thing. So internally tangent circles, even though one's inside the other, they are not concentric. Externally tangent circles means they are outside of each other, but they share a common point. So let's take a look at this. We have two externally tangent circles here. So we're going to find the length of each radius, identify the point of tangency, and write the equation of the tangent line at this point. Well, looking at circles S and R, you should be able to count the length of each radius. You should get that the radius of circle R has a length of 2, and the radius of circle S has a length of 1.5. Now look at where these two circles meet. Their point of tangency is at -2, 0. So if we have a tangent line going through this point, in this case it will be a horizontal line, and all horizontal lines have y equals and where it's intersecting the y-axis. So the equation of the tangent line at this point would just simply be y equals 0. So be able to identify the length of the radius, the point of tangency, and the equation of the tangent lines of tangent circles. You also have common tangents with circles. A common tangent is a line that is tangent to two different circles. So the two diagrams here, the ones in red, those are common external tangents because you notice they stay outside of the two circles. The blue ones are common internal tangents. Notice the blue lines go in between the two circles. Therefore, they are internal tangents. We have some theorems we need to look at. This first theorem says if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. Simply that, if a line is tangent to a circle, the line is perpendicular to the radius. The converse is also true. If we know that a line is perpendicular to a radius, then we know that that line is tangent to the circle. So let's take a look at how this can help us. Let's look at this word problem. Early in its flight, the Apollo 11 spacecraft orbited Earth at an altitude of 120 miles. If the radius of the Earth is approximately 4,000 miles, what is the distance from the spacecraft to the Earth's horizon to the nearest mile? So first you got to draw a picture. So we have circle C representing Earth. If the spacecraft was orbiting the Earth at an altitude of 120 miles, you should note that ED is 120 miles. We're given that the radius is 4,000 miles, which is CH. We need to find EH, which is the distance from the spacecraft to the horizon of the Earth. So first we need to use our segment addition, knowing that EC is CD, which is the radius, plus the height or the altitude of the spacecraft. So when we substitute in our numbers, we get that EC is 4,120 miles. Now since we know that a tangent line is perpendicular to a radius, it does create that right triangle. So if we know two sides of a right triangle, we can use Pythagorean theorem in order to find that missing side. To where we get that the distance from the aircraft to the Earth's horizon is approximately 987 miles. So I want you to take a look at this question. Kilimanjaro, the tallest mountain in Africa, is 19,340 feet tall. Still using 4,000 miles as the radius of the Earth, what is the distance from the summit of Kilimanjaro to the horizon of the Earth to the nearest mile? This question will be due in class. Remember to draw a picture. Draw the Earth, draw in the radius, draw Kilimanjaro. The summit is referring to the top of the mountain, so you're wanting to know the distance from the top of Kilimanjaro to the Earth's horizon. Remember to do this and have it ready to show me in class. Another theorem we need to discuss is that if two segments are tangent to the same circle and they're from the same external point, then those segments are congruent. So in this diagram here, since AB and AC are both tangent to circle P and they both come from point A outside of the circle, we know that AB is congruent to AC. So here, HK and HG are tangent to circle F. They want us to find the length of HG. Well, since they're both tangent to the same circle, they both come from the same external point H, we know that HK equals HG. So from there we can substitute in our values that we know, and we get that A is 12. But since they wanted us to find the length of HG, we need to go back and substitute 12 in for A. And we get that HG is 28. Something good you should always go back and do is to check your answer. And if HG is 28, then HK should also be 28. So if you substitute 12 into HK, you should also get 28. So 5 times 12 is 60, minus 32 does give you 28, so you know you did it correct. It is important that you check your work to make sure you get the right answer. Now I want you to take a look at this one. Given that RS and RT are tangent to circle Q, find the length of RS. This one will be due in class. Make sure that you set up your equation, solve, and go back and check your answer to make sure that you are correct. Remember that this is due in class.